Now it's time to get down talking about specific systems. We're going to look at EVAP, one of the main things tested by Mode 6. Mode 6 is going to check the system for flow, looking to see if it's normal flow with no restriction. Then it's going to check for leaks. It's also going to process and check to see if the canister purge is leaking and separate a leaking canister purge solenoid from normal leaks and check for restrictions caused by dirty canisters or blocked vent solenoids. If the test, in these tests, it's going to show us the results the last time the monitor ran. Now, the last time, let's talk about that. Prior to 2001, GM, for instance, wants to see the vehicle set at least 6 hours. That way it knows the temperature of the fuel in the tank and the amount of vaporization that will be taking place. And the temperature must be between 40 and 95 degrees at the time the vehicle started, and both the intake air or the ambient air and the coolant temperature must be very close to each other, 10 or 15 degrees. That means you're going to get one chance to run this in a day, and it's not going to be a vehicle sitting outside in the wintertime on a really cold day where it's below 40 degrees when it starts up in the morning. So the last time this monitor ran may be a long time ago. Some monitors may not have run recently, and Mode 6 data will be very old. To give you an example, we had a problem we detected in December doing some testing. We created the problem, won't go into all the details, but we broke a solenoid, a leak detection pump on a Chrysler to be specific. And we didn't get 2 consecutive bad trips until March, 4 months later. So all the data you would have seen may have been very old. And let's just take a look at Mode 6 for EVAP on GM. There are 3 different test IDs and up to 30 different SIDs for each one of these test IDs. There are over 350 TIDs and SIDs for GM alone. You got a lot of years crammed into this thing. Now, what we said again, what are we going to be testing for? Purge vapor management valves. Vapor management valves on Ford, purge solenoids on GM and Chrysler. The canister itself, does it flow freely? The vent solenoid, does it open and close as it should? And the fuel tank pressure sensor, can it read fuel tank pressure accurately? And when it reads accurately, what's the normal results we're going to be seeing during operation? Now, Mode 6 identifies the failures and allows you to focus on the root cause of the failure instead of testing the complete system. When we get a leak code, it's the same for everybody, little or big, 20,000s, 40,000s. We're going to show you some other codes. And we're going to help you increase your diagnostic accuracy and speed so you can be more productive. Now, the purge solenoid is normally closed. This is something you need to know. The vent solenoid is normally open with the exception of Chrysler's natural vacuum leak detection we'll talk about much later. Part of the EVAP monitor will test the purge solenoid to see if it can seal the system, looking to see if it can leak. You can take advantage of this technology by looking at the Mode 6 data for the purge solenoid test and the other information in here, see if there's pending problems or if it has passed easily. Let's talk about how things are going to work. We're going to go study the screen of the scan tool to find out what's going on. What's the TID? What's the SID? Did it pass, fail? What's the maximum? What's the minimum limit? Those values gives us a lot of data. Once you have the Mode 6 data, you're finished with the scan tool until you need it for diagnostics. The test results and the limits in the scan tool are going to tell you exactly how the system is performing. Now, this is an example of a test ID. We're going to be testing for flow, leaks, leaking purge solenoids, blocked vent valves, other restrictions. We're going to be doing this in Ford, GM, and Chrysler. Right now, we're going to focus on GM. This is a GM schematic. Depending on the vehicle manufacturer, EVAP may point you to a specific test, or it may not. Ford has some phases that look a little strange. The pieces we're going to have functioning is the purge solenoid. Remember, it's called a vapor management valve on newer Fords. Fuel tank pressure sensor, common to GM and Ford. Necessary, and it has to operate properly for this system to work. This is the vent solenoid, and just under our hand here is the actual filter for that vent solenoid. Remember, to be sucking dirty, dusty, nasty air in from outside, and can get to be dirty and nasty in certain situations. Here's your service port where we put no more than 1 psi of pressure during our testing. What's going to normally happen is the fuel tank is going to build up vapors, and we'll show this roughly by our yellow here, and it's going to force its way into the canister to be stored in the canister. It's going to have to go through the canister out through the vent solenoid, which is normally open when the engine is shut off. Those vapors are absorbed by the charcoal in the canister. The normal vent solenoid lets it vent easily and will only be closed when we're going to be testing the system for leaks. It is going to allow the fresh air to enter the system when we decide to pull air in during purge. Now, the PCM is going to decide when to do purge because purge has a number of rules. It activates the purge solenoid when it's ready, and then it's going to use engine vacuum to draw vapors into the intake. Now, if there are vapors, this is going to change the fuel mixture slightly, and that's part of our testing. As they go into the engine, if we have extra vapors, we're going to have to offset those extra vapors. So we're going to have to do some testing, and the PCM is going to have to do some checking to see just what's coming out of this canister. The canister is looking here. You see this nice, clean, pristine canister. They're beautiful things. Let's look at TID2 EVAP monitor, and OA EVAP monitor, and 85 EVAP monitor. Why have we got so many TIDs for EVAP monitors? Well, it covers a dozen model years or so, and there's different model years, different car lines, use different TIDs. Looking at some examples. TID2, SID 8424. Both of those testing the same thing. Remember we told you when the ending digit is the same, they frequently are testing the same thing? This TID and SID relate to a test that will determine if the canister is loaded with fuel vapors. Loaded canisters have fuel vapors and increase the richness of the mixture when they're vented. It's that simple. We'll show you the test in more detail. TID 2, 6, 26, 36, 46, 66, 86, C6. They determine if the system has excess vacuum. What could cause excess vacuum? Restricted systems can have higher than normal vacuum. If we have dirt plugging up our canister, crimped hoses, or if we have a clogged up vent solenoid, these can all cause the vacuum to be higher than normal. TID 2, SID 10, 20, 30, 40, 50, 60, 70, 80, 90, CO, DO. These systems cannot hold a weak vacuum. What happens is we close the system up and try to pull a weak vacuum. Systems with gross leaks will not be able to develop a weak vacuum. It's leaking out faster than we can build it up. We're going to use the fuel tank pressure sensor. We'll show you more about that in a moment. TID 11, 21, 41, 71, 91. They determine if the EVAP solenoid is leaking. How can we determine if the EVAP solenoid, in this particular case, we're looking at a vapor management valve, switching them around just to keep you on your toes? A sealed system will show increasing vacuum if the purge is leaking. How do we seal it? We close purge, we close the vent, and we watch the fuel tank pressure solenoid, pressure sensor. We'll cover all that in detail. 12 and 52, small leak in EVAP system was found using the vacuum decay system. The size of the leak will determine how quickly vacuum leaks down on a sealed system, and we'll talk about that in detail. Small leak using natural vacuum. We cannot build a weak vacuum during the natural vacuum test if we've got a small leak. So what's the advantages of breaking it all down like this? Well, the monitor divides the whole system into separate parts of testing. It allows you to test quickly and identify what failed. For instance, as we talked about, TID 2, SID 11, 21, 41, 71, 91 indicates the purge valve is leaking. Knowing this, you can test the purge valve without having to test the entire system. Because what happened once the EVAP is determined the purge valve is leaking is it looks no further simply because it's not going to be able to go beyond this. It can't test for a leak because it's already determined a leaking purge solenoid. We're going to show you exactly how this works with voltages in just a moment. I want to get you the idea of what's happening in the EVAP system first. We're saying during normal purge, if there are fuel vapors in the canister, the oxygen sensor should indicate rich momentarily. Now, we're going to show you exactly how the PCM does it. It does it very carefully. But if there are no vapors present, the oxygen sensor will go lean. Let's stop and think about that. If we've got fuel, we can see the fuel. Makes sense. It goes slightly rich. We're going to show you the strategy used by the PCM to crack this open just a tiny bit before we open it all the way up, so we'll know what we're working on. So don't get concerned you're not going to be able to figure that out. The PCM, during normal purge, the PCM will make fuel trim adjustments to compensate for the addition of fuel or air, depending on whether they have loaded canister or not, by adjusting the injector pulse width of the injector. So it's going to go in, we're going to show you the strategy of how it picks it up, and then how it makes adjustments. This is done so that the customer or the motorist feels no drivability impact. Now, there is no single test used for EVAP. Each manufacturer has designed a monitor that's going to test for leaks, flow, the various components and restrictions. We will use the information we created for TID and SID identification to tell you what's going on and hopefully help you understand the definitions so that when you read something, you'll understand what they're talking about. This is our digital scan tool, our PC-based scan tool. Each one has their own display. We notice a lot of reds here. Different things are showing up. We'll go look at some of those in details. Here it is on an OTC, and here it is on an Auto Ingenuity. Different vehicles we're testing here. Regardless of which one we use, it's done in a certain order. Each manufacturer has their own tests, but they're all going to wind up doing the same thing. Let's get down to understanding the EVAP system first. And the first thing to understand is what a weak vacuum is. These weak vacuums are measured in inches of water. 1 inch of mercury, which we normally see on our vacuum gauge, equals to 13.6 inches of water. Now, we rounded that up. You can use the 13.595097 if you like, but we have found 13.6 to be more than sufficient. In fact, you can even round it up to 14 if you want to. It's not that critical. It's what the point we're making is that inches of water are much smaller than inches of mercury, which you're accustomed to. We keep saying weak vacuum. We're talking about a vacuum measured in inches of water, not manifold vacuum like we get measured in inches of mercury. You can keep this, but there's an easy way to build this. It's really how many inches of water moves in a column of water, and it can be done quite easily. The loaded canister we're talking about has fuel vapors in it. So during normal purge, the PCM determines if there are fuel vapors or air in the canister, and then makes appropriate adjustments to pulse width and to short-term fuel trim. We can do our own test. We will do it, not depend on the PCM. Here is a test. We're driving down the road. Now I want you to look at several things first. Notice that short term on the left is moving around quite a bit. What we're going to do is we're going to wait to very specific things. Look at purge. It was at 0%. Then at the dotted line, it goes to 12%. Notice short-term fuel trim. It was up about plus 2.3, and the same moment we changed this, it dropped to minus 3.1. That's about a 5% change. Now, the way you use grafting in this advanced grafting technique is you look at something the same instant EVAP changes, what happened to short term. You can't evaluate short term up there to the left when EVAP was off. Now, we don't turn EVAP on to typically we get around 155, 170 degrees Fahrenheit, somewhere in that range. It's called secondary fuel trim. Till we get into out of cold enrichment, which is the automatic choke function of the PCM, we don't do any EVAPs. EVAP comes on once we know everything is settled down, the engine's running normal, then we move into it, an EVAP, open up and have a look at it. The PCM now knows exactly how much fuel it's getting. It had to change fuel delivery 5% for just a little bit of opening, 12% on our canister purge duty cycle. So the strategy is to open it slightly, then know what your adjustments are. We know we have fuel vapors, so it knows the hoses are connected to the canister. The EVAP is working somewhat. It may not have it may have a small leak, but it doesn't have hoses that are off, and the solenoids are in fact working. The canister is hooked up, and we can see it. That's all it means, but that's an important step to take. Now, here's another one. We're going from 19% canister purge up to 50% canister purge. Short-term fuel trim was minus 3.1 before, jumps up to plus 3.1. We moved 6%. 6% more fuel. Now that's a big step. The canister is not loaded. We are seeing air. Now that doesn't mean the canister is broken. It just means we can't say for sure it's connected. We're going to have to do another test, and that's what the loaded test is going to do. It's going to first determine if it's loaded with vapors. And we're going to adjust purge to be much smaller if their vapors are present. We're going to verify things. What should purge be? Well, what were the results of the loaded canister test? If this test does not run, the PCM does not pass, the PCM will do a weak vacuum test. If we can't see vapors, then we do a weak vacuum test, and we'll talk about that. Here's our weak vacuum and purge test. Let's start talking about numbers here. We're going to start off looking at our purge weak vacuum leak test. We have two scales. The red scale here is pointing to 0 inches of water. We said this is weak vacuum. And at this point, we should have 1.4 to 1.6 volts at the fuel tank pressure sensor. Now, one of the things we told you is we wanted to make sure the fuel tank pressure sensor measured accurately. We have had issues back when they first came out in 99, 2000, 2001, where they were inaccurate. So this is an important test. We're looking for nominally the middle number of about 1.5 volts with a little cushion around it. This tells us we have no vacuum and we have a normal fuel tank pressure sensor. Now, if we build pressure, the numbers go positive and the fuel tank pressure voltages go down. If we get down around 4 inches of water positive, we're down around 0.7 volts. If we have a vacuum, on the other hand, we're going to go up. So if we get up around 2.4, 2.45, we've got about 4 inches of water vacuum. So this is what we're looking at. We're going to control it. We're going to do our standard testing. If we don't think it measures accurately, we're going to come in here. We're going to measure voltage, measure ground, measure the signal. If volts is good, if pin C reads 5 volts, if pin A reads under 0.5 volts, and we cannot read engine off vacuum to be sure we can remove the gas cap accurately, change the fuel tank pressure sensor. It's that simple. So we've verified our pressure sensor. We fixed the ones that are broken. We've done a purge leak test. To do this test, the purge solenoid is closed. The vent solenoid is closed. The system is sealed up for a few seconds. Now what you see here, in our case here, we're staying right around 0 inches of water. No pressure, no vacuum. Very minor changes. If we have a failure, well, if the purge solenoid is leaking, it won't seal off manifold vacuum. Since it cannot seal manifold vacuum, the vacuum is going to start creeping up after a few seconds, and we will set a code for a purge solenoid that's leaking. This is why this is such a good test. Why it's nice to look at this and know for mode 6 that the purge solenoid is the source of our leak. If the FTP, fuel tank pressure, increases voltage, the purge solenoid has to be leaking because the vent is sealed. And if it's sealed, there should be no vacuum coming in, no air coming in. So this is our failure. We measured it. If it fails, it goes no further because nothing can be tested. It's just going to measure how many seconds the vacuum switch is closed on older systems to see if it's leaking. It's going to try to pull a vacuum, close the solenoid, and see if the vacuum switch stays closed. That's all it's going to do for a weak vacuum test. The next question, if we can't, can we pull a weak vacuum? When we close the vent, can a vacuum be pulled by duty cycling the purge solenoid? The vent on the right is going to close up. PCM is going to duty cycle the purge solenoid for a few seconds to see if we can develop a vacuum. We first passed our purge solenoid. Now we're going to start going up. Our target, somewhere between 265 and 330 volts. That's our target vacuum and our target voltage. The purge solenoid's been duty cycled. The vent solenoid is sealed. If we can't pull it up in this target range, we fail the weak vacuum test. We have a gross leak. See how easy this is once you know what you're looking for? And we know the voltages we're looking for. Is there a restriction? Is the system flowing freely? Here's two examples. One on the bottom. Purge goes up to 12%. We're looking at fuel tank pressure. Its average is 145. It varies between 143 and 147. That's as close as you can get to 145. But notice at the top, we're varying between 237 and 220 with the average of 2.27 volts. The top system has a restriction either in the canister, in the vent, or one of the lines is crushed. It's that simple. We're done. Now it's simply a matter of disconnecting the vent. If it drops back to normal with canister purge running, we have a bad vent. If it still stays high, we can disconnect the canister. If it drops down, there's probably liquid in the canister. Sometimes we get moisture accumulation in the canister that particularly causes problems in the wintertime. What you might want to do is take some very low pressure air, turn the canister upside down, and run some dry air through it to get this moisture out. Be warned, it's dirty, nasty, rotten stuff. What's wrong with the moisture if you don't get it out is it'll eventually deteriorate the carbon granules, the charcoal, and it'll start sucking it through the system and into the purge solenoid and block the purge solenoid. So restrictions get to be important. Here's the overall thing. Here's start to finish. We started off at 0. We closed the vent. We closed the purge. When it's warm weather, we might get a little pressure rise. You might see it dip down a little bit. If the dip is too big, it'll abort the test, but this is just checking to make sure everything's known. Then it's going to start purge duty cycling, pull a weak vacuum, stop, hold it. Purge solenoid and the vent solenoids are both closed. Then we're going to take our first reading and start recording with our vacuum and take a second reading out here and determine the amount of voltage drop, which equates to pressure drop. Then we're going to open the vent. Now watch what happens. Watch for a rapid release in vacuum when we open the vent. This is called the vacuum decay restriction method. If you've got a vacuum and you open it up and it does not decay quickly, this is a test used by the PCM in Ford and GM to determine you have a restricted system. So now that we see the overall chart, this makes testing pretty easy. It's not hard at all. What do failures look like? Well, failures, the first arrow on the left, we're starting to build vacuum. We won't go any further if that happens because that's a leaking vent solenoid. Second arrow, vacuum may not reach its target. We failed the weak vacuum test. It couldn't pull it high enough. The third arrow on the right, the vacuum K is too high. We've got a leak. So any one of these three could give us a P0440. Mode 6 will divide this into different pieces so we know exactly what failed. Ford, we're going to do similar tests, but the difference is we're going to be using a solenoid, a fuel tank pressure sensor that goes from 280, 265 downward as we have vacuum, going above 265 when we have pressure. The system is the same. We're going to have a variable, a vacuum management valve is going to be duty cycled to a weak vacuum. We're going to close the variable management valve, take our first reading, second reading, do our decay, do everything we just did in GM, only now we're going the opposite direction. When we have a restriction, the numbers will be too low. In GM, we had a restriction. The fuel tank pressure sensor voltages were too high. So the first thing we do, just like we did before, our purge or vacuum management valve test. Did it seal? Yes. Then we go down and do our weak vacuum test. Did we get to our target? This case, about 150, 165. Then we do our leak test, take our first reading, second reading. Here's what a failure looks like. We couldn't, vacuum bleeds up too quickly. We got a large leak, 40 thousandth leak. Here's a gross leak, 455. We duty cycled up to 99% on the variable, on the vacuum management valve, and we couldn't reach our maximum, our target vacuum, 150, 165 range in voltage, 6 to 7 inches. Here's a blocked vent solenoid. What's happening here? We get down to about 11 inches is where the filler cap will vent vacuum. It goes down, vacuum relieves, builds back up, goes down, vacuum's relieved. It's a blocked solenoid. Can't be controlled. The leak detection pump is usually located somewhere near the fuel tank. It's going to use pressure instead of engine vacuum. Other than that, it's going to work very similar. What's unique about Chrysler is the way they've organized their Mode 6. It is a TID-based Mode 6, meaning it's going to be mainly by system, and then the SIDs are going to indicate what happened. A SID 80, for instance, indicates there is a minimum limit. A SID 0 indicates there's a maximum limit, and SID FF indicates the test did not run completely. It's partially complete, but did not run, not pass, not fail, just incomplete. Here's the way the system's going to work. We have manifold vacuum applied up here at the vacuum source in the top left. We have a return spring that's pushing down on the diaphragm. The diaphragm will be pulled up when we apply manifold vacuum. When the diaphragm pulls up, it closes the vent seal on the bottom. And once the diaphragm is pulled up, it closes the switch on the right. These four things work together to make this a pump. It's very simple. We pull it up, the spring pushes it down, it pumps out pressure. Since the seal is closed, the pressure goes back into the EVAP system. How long it takes it to pump it up all depends. Let's go through and see how things work. This is the wiring for the switch and the ground and the power for the vehicle we're working on. Make sure you use a very specific system because it's very important that you don't ground the switch. But we can ground the ground control to do our own testing. This is the actual diaphragm we pull up. The piece in the middle of brass comes up, makes contact with the switch. The spring is going to push this diaphragm back down, which is not shown in this case. So what's going to happen is we're going to apply a vacuum source here. And then we're going to decide when it's necessary. We're going to open the control valve like it's shown now. That's going to apply vacuum to the top of the diaphragm, which is going to pull it up. And when it comes up, the speed pump switch is going to close, and the PCM is going to say, okay, I'm going to unground the control solenoid, let it close. The spring pushes the diaphragm down. Since the vent on the bottom is sealed, it'll push pressure out, and the system works that way. The light-duty spring is going to push it down, and this spring is a calibrated spring. The pressure builds up to about 7 inches of water, which is what we've been looking at in the other system. This is where the spring is going to stall, the diaphragm is going to remain open, and the scent switch is going to stay closed. How long this switch stays closed is determined by the size of the leak or lack of a leak. So this signal is going to be the signal used by the PCM to determine there is no leak. If we have a leaking vent or anything else in here, or if the solenoid gets dirty, doesn't actuate properly, all these things can produce failures. If the pump stalls when the pressure builds to approximately 7 inch, everything is fine. Then we're going to see if it'll hold. If it doesn't hold very long, it sets a TID 61, SID 80, 40,000 leak. If it holds for a little while, but not as long as it should, it sets a TID 62, SID 80, 20,000 leak. If it doesn't leak down, it passes and we're done. So all of those things work normally. But we have a new system on the horizon. Because we had the situation where we could not always get the test to run between 40 and 95 degrees at startup, a new system was developed. Natural vacuum. A vacuum in automotive terms is a low pressure that is below atmospheric pressure. Just so we understand that. It is not truly a vacuum, and we're talking very weak vacuums here. The natural vacuum testing relies on the expansion of fuel when it's hot and the contraction as it cools. Pressure and vacuum are directly related to temperature. You heat up gas in a sealed container, it will expand and build pressure. Cool gas in a sealed container, it'll create a vacuum. And that's the technique we're going to use for natural vacuum. It's no more complicated than that. This test runs after the engine is turned off on GM and Ford. What we're going to do is the system is sealed up. If we've been driving long enough, if the fuel is warm enough, evaporating fuel vapors will cause fuel tank pressure to increase when it's warm and then to decrease as it cools. PCM is going to monitor the pressure and vacuum caused by this expansion and contraction of the fuel, and we're going to do some special steps to make sure we've identified it. The PCM watches pressure increase after shutdown. If there's no pressure increase, the test is aborted. It'll wait and do it again. It's going to keep track of this and eventually do a weak vacuum test if it cannot see a pressure build. If there is a pressure increase, a decrease must follow if we have no leaks. After the increase, the PCM will vent the system quickly. This is called a re-zero. And then it's going to seal it back up and watch for a decrease in pressure after cool down. We know it went up because it expanded. Now let's see what this looks like in voltage on our fuel tank pressure sensor. First, we see the first part of the pressure increase. Now notice in the pressure increase, we see it building gradually and then finally flatten out. That flat portion down there where it levels off tells us the expansion has stopped. When the expansion stops, the pressure levels off, we're down around 0.6, 0.8 volts, plus 4 to 5 inches of water. Ford looks for 5, GM looks for, they say, around 4. So what's going to happen next is the PCM is going to open the vent to zero it, then seal it back up. What we've done, we've had fuel that's expanded, we've zeroed it out, let the pressure off, now seal it back up, and we're going to wait. As we wait, when the full fuel cools down and volume decreases, the vacuum increases. This is a natural vacuum formed as the fuel cools. If we never see the vacuum form, we've got a small leak. If we never see the pressure rise, we may have a gross leak. The system will then go do a weak vacuum test. So we're going to do our canister purge, leak test. We're going to do our weak vacuum test, but we're not going to do the running leak test. We're going to do the leak test at the end. So all we've done is change the leak test. We're going to use the same components and put it at the engine shut down and let natural vacuum take place. The natural vacuum cycle is to let the vacuum build up, plateau, release the pressure, zero it out, watch for the vacuum to build up, and the vacuum will tell us. We're all going to be based on fuel tank pressure voltage, watching an increase and decrease. Ford works the same way, with voltage going in the opposite direction, and they're going to divide it into a bunch of different phases. They're a little more organized. Now, Chrysler has a different natural vacuum test. Chrysler's natural vacuum test uses a solenoid to bypass some check valves. The solenoid is turned on when the engine is running for a normal purge. That removes any restrictions. If you're going to do smoke testing and want to use restrictions, like we're going to show you how to do, what you should do is supply battery voltage to pin 3 of that solenoid as shown in this schematic, because its pin 1 is grounded. That will turn the solenoid on and you'll have no restrictions. So this is the exception. This natural vacuum has a built-in restriction. They're check valves. Let me show what those check valves look like. The vent is normally closed. It's only open when we turn it on. When it's turned on, it bypasses the check valve, and we do that when we're doing normal purge. Let's look at the 2 check valves. First is a pressure relief. Pressure relief opens at 1/2 psi. This is really small pressure. This is a large area diaphragm or check valve. It enables refueling with the vent closed. The vent solenoid can be closed. This will let us refuel. If you have problems refueling, pump frequently kicking back, not releasing the way it should, this has probably gotten dirty and is no longer operating properly. You may also at the same time find you have a leak problem indicated. So what this is going to do for us, anytime we have a pressure, this is going to vent it off and keep pressure at almost zero, just slightly below. It's going to keep pressure low, so it doesn't have to turn on and re-zero like GM does. This solenoid will re-zero for us automatically. The pressure vent holds pressure low as the fuel expands. It seals the system when pressure starts dropping. Let me say that again. It's going to relieve the pressure as the fuel expands, and then it seals back up when pressure starts dropping. With the system sealed and the solenoid not on, we're going to wait and watch this switch. The vacuum switch closes when the vacuum develops. The time it takes, the PCM times how long it takes to see the vacuum as indicated by the natural vacuum switch. It can go some very long times. This switch normally closes at around 1-2 inches of vacuum. So the